All right, everybody. So here we go. So this first one, it gives you uh, some extra information, and it just gives you a test statistic with a z-score. So you could put that in the normal CDF. It's right-hand tailed, so it's normal CDF, right? And if we draw it out, we get 0, we get 1.4 over here, and then we want to find this area. So it's normal CDF 1.40, and then 9999, however many nines, and then 0 and 1. And since it's a z-score, I don't need degrees of freedom, and then that'll pop out that answer. So on this next one here, we got an answer of C. And so we talk about this information from the colleges. Here's my H of O versus a less than H of A. Prior to the study, the estimate of power that their test against the alternate hypothesis is 0.85. That means we're looking at the probability of rejecting the null when the parameter is actually 900. So that's the probability of rejecting it. Remember, that's the whole idea of power. What's the probability? The probability of rejecting H of O. And it's actually rejecting H of O. Okay? So notice how that is not H of A. It's when you reject H of O because there is evidence for H of A. Okay? So it's an alternative. So it's the idea that we rejected H of O when H of O is not true. So we're getting the correct answer. All right. So let's look at the next one here. So we've got mean time. Mean, we're automatically at mu is equal to 25. That'll be our H of O right off the bat. So we know that. So this one's gone, just because of the less than. New ingredient is added to speed up, denote the mean time to obtain pain relief. An experiment is conducted to verify if the new product works more quickly. More quickly than 25 minutes would be less time. So H of A has to be mean time is less than 25. Because if it's slower, it's going to be greater than. Okay? So if we drew that out, 25, statement of no difference. This is faster. This is slower. Because it takes more minutes to do. All right, so let's see here. Let me move this out of the way, guys. So let's see here. Test of mu is 60. I always have to write them out. So that means that when we're looking at this, my mu is 60. We have 58 as an x bar. So this side here, I would read it as 0.04, but it is a difference. So you're going to have to multiply 2 times 0.04, which gives you 0.08. So that's very interesting that they give you this answer right here, that there is sufficient evidence to conclude. I don't know, guys. Either way, I guess that'd be the only correct. And no, see, I would say that there is insufficient evidence because if a sample means this and a p-value, I don't know. I guess you could go either one. Either one would be correct in my eyes. So I would say multiply it by 2, but according to the answer, they didn't multiply it by 2. So it would be 0.04 is less than 0.05. So therefore, there's sufficient evidence. We reject H of O and assume that H of A is different than 60. I don't know. I disagree with that one, guys, but oh well. Because T procedures are robust, the most important condition for their use is that data can be regarded as a random from the population. Okay, so robust means that we're not sure if they violate the conditions, that they satisfy all the conditions, And so the most important condition is that it's random from the population. Because if it's random from the population and it's close to normal, we're okay. But if it's not random, we're out of luck. So random is always the most important piece, especially with idea that they're robust. All right, let's look at this one. We want to test H of O, and they give us a confidence interval. So the confidence interval shows 1.4 and 3.6. 1.5 is right here. So it's in the range for fail to reject. So we fail to reject H of O, and so we fail to reject. All right. So remember, when the claim is inside the confidence interval, we fail to reject. Let's tackle this next one. We're talking about paired data, which is the express lane problem. Remember, we did express lane minus regular lane, and we got the X bar of the difference, which means that was all the differences added up, and then we did the normal plot of the differences, so it's only B. We only check the differences in there. Now, all these other answers have to do with the next chapter. Type 2 error in this setting would mean what? That not concluding that the diet leads to weight loss when it actually does. So a type 2 error in this particular piece right here, so we're talking about this one, is we're going to do, so if we fail to reject, type 2 means fail to reject H of O. So not concluding weight loss when there was. So if we fail to reject and there was. So that's kind of the issue with that one. Remember the number 2 and the number 2. A researcher wishes to determine if people are able to complete a certain pencil and paper maze. So here's our info that we need. There's 40 seconds without music. So we have an X bar. So let's draw this thing out here. We have an 40, and we have one to the left, which is 39.92. Okay. And that p-value is 0.0002.02. Which statement is appropriate conclusion? So basically, although the researcher got a significant result, it appears to have little practical significance. So the whole idea is that they can complete a maze, right? And so 10,000 people complete the maze with classical music playing. And so that doesn't really do much for us. We can complete a maze faster. So there's really no practical piece that we need to worry about unless you want to tackle mazes faster. Okay, so which of the following statements is or is not correct? The power depends on the alternative value. Remember, power is rejecting H of O when H of A is true. So we reject H of O when H of A is true, so we need an alternate value. So we got number 1, the probability of type 2 error is equal to the significance level. That is definitely false. Error probabilities can be expressed when the significance level has been specified. Yes. So your errors, you need a significance level, because remember, type 1 is equal to the significance level. So that means that you have to have the probability errors after you take significance level. So that's our answer there, because 2 is completely wrong. publishing scientific papers online is fast. So here's that idea. 72 out of 104 people said yes. So that is a ZAP problem. It's a ZAP problem. We want to know if it's more than, so there's our greater than piece, 67, statement of no difference. So if I'm going to draw this out down here, we have 0.67, and then we have 72 divided by 104, which is 0.69, and we want to know the tail on that thing. So that means the z-score is greater than 0.43. Okay, so that's how you use this to decide which way you're dealing with. So if you're going to do normal CDF, this is your lower boundary, and your upper is 9999. That's kind of the key piece on that one. All right, so don't forget, you state both, and then you state what the proportion is. Significance level, if it hasn't been said up there, is automatically 0.05. The procedure is a one sample z-test for a proportion. Check for random. Check your n times p. Don't forget we're using our statement of no difference right here. And then from there, our independent, we can assume that there's more than 1,000 recent articles. So at one point or another, you need to state p hat. And since we're using it, it's the only spot we use it is right here. I would state it right next to this in the do part. Set this up. Don't forget, this is going to be stat minus parameter over the standard error. These words are on your formula sheet. This is in your formula sheet. So you got to pull it all together. Don't forget to state the p-value is greater than 0.05. And if it's greater than, we fail to reject. Excuse me. Oh, big yawn. There is not sufficient evidence to conclude that the proportion is greater than 67. So we're just kind of restating the question that they ask right here. Okay? Interpret the p-value. Just remember that the p-value, assuming that 0.67 is true, is finding the probability. Finding the probability that it's greater than 0.69%. So the idea is if the true proportion is 6.67, the probability of getting sample proportions farther than 0.67 is 0.0336. So we're just saying, what's the probability of getting that extreme value or greater? That's all we're saying. All right. So here's a list of 10 bags here. 75% of the bags of the potato chips produced will be above 32 ounces, right? So they adjust the machine of the first quartile, Q1, to the sample weights to be lower than 32, which makes sense because if we look at this here, here's Q1. We want everything greater than Q1, which is 75%. And then here's the other 25%. So we want all bags greater than 75%. State the value of Q1 for this sample. So we deal with our sample. You can put it in a list, rearrange it, whatever you need to do. And the Q1 is 30.8. We set our bar at 32. Remember Q1 right here. So if I redraw this, Q1 is equal to 32. That's our H of O, right? Technically, that's what we want. and 30.8 is down here. So yes, the manufacturer should be concerned because it's less than 32. So if we state it, then we state H of O, the true Q1 is 32. And since this test statistic is on the left, we want to know if the true Q1 is less than 32. That's how you set it up, because here is our Q1. Let me rewrite this here. Sorry, guys. This is our mu of Q1. Our mu of Q1, we wanted at 32, but we got a test statistic of 30.8. So we've got to find out the probability over here on the left. That's pretty small, okay? So is it plausible that they come from a normal population? This is a normal probability plot. They're pretty much in a straight line. So that's why it's roughly linear. So it's reasonable to assume that they come from a normal population. So just make sure that you know the normal probability plot or the dot plot. All right, so let's tackle this here. So we're dealing with Q1. So we've got this piece up here, and now we've kind of reset ourselves. And we have a simulation of 100 random samples of size 10. So we know our N is 10, right? May not even worry about it. We may not come into play. All right. Now that's, our N is 100. So we're generated from a normal population with a Q1 of 0.32. So our Q1 is 0.32. That's our middle. That's our mu of Q1. Q1 is equal to 0.32. The sample for Q1 of these is computed and displayed. Use the results of the simulation to test the hypothesis in part B. So here's our part B. We want it less than that. So we come over here to 30.8, right? 30.8, 0.6, 0.7, 0.8. And I've got 2 here. 2 out of 100 is equal to 0.02%, right? So there's only 2% that are lower than that. So since the p-value is small, we reject the null hypothesis. We reject the null hypothesis. This is no longer true. The company should adjust their machine because it's not at 32. It's not working very well. Okay? Oops, I didn't. Yeah, you guys saw that. Okay, so we're testing mu of 32 against our test statistic of 30.8. It's just like the one we did. There's 2 outside. So that's 2 divided by 100. That's 2%. 2% is less than 5%. So we reject. We reject the null hypothesis. The true Q1 is not 32. So that means since they wanted it at 32, because they set it at 32. They should have concerns, and they should actually adjust their machine so it is at 32. All right? Okay, guys. Good luck. Talk to you later.